first problem is that there isn't enough platinum in the world. It's one of the rarest metals. I think there's something like 60,000 tons of platinum available in the world.
Mhm.
And we don't nearly have enough to sustain a full hydrogen economy. So one of the approaches that are currently emerging, getting more exciting, is having two metals instead of one, with one metal sort of anchoring the iron. But to me, we are at least we need massive government support, and we're at
Mm.
least a decade, I'd say, easily a decade away. It brings the question of when do we start to scale up materials? It's more than how do we do it, but at what point is it sensible to do it? We may have, say, 100 research papers, and while you can train the AI on that 100, you may not get information that's actually scientifically accurate or the information you're looking for.
My today's guest is basically the James Bond of hydrogen fuel cells, minus the tux plus PhD. Quentin Meyer is a leading voice in green energy innovation with over 70 scientific papers, a PhD from UCL, and the presidency of the Fuel Cell Division at the International Association for Hydrogen Energy. He's been quietly shaping the future of clean power, from micro scale imaging to turning lab breakthroughs into real world tech. Quentin's work is where science meets solutions. So, if you ever wondered what it really takes to make hydrogen energy work, this is the guy who actually knows. Quentin, welcome.
Thank you for the introduction, and thanks for the very elogious terms about this.
There's this huge promise that fuel cells will power the future, but
Mhm.
we're still not there. Why is
Yes.
that?
So to me, I've been working on fuel cells now for over a decade. The really interesting thing I found is that people have talked of fuel cell powering the future, but a really big issue I see is that people didn't think of what future it was going to be. In what sense? In the sense of it is there's been a lot of trial and error with a lot of different failures of what fuel cells are going to be used for.
Mhm.
So for quite a while, there was fuel that followed basically how the technology evolved. So there was a lot of fuel cells for very small scale application, mainly because companies didn't know how to make large fuel cells yet. So there were talks of fuel cell for battery charge. There was at some point a debate for battery fuel cell phone chargers versus fuel cell batteries chargers. That didn't go very well because people didn't want to carry a hydrogen cylinder with them to recharge the fuel cell. And then there's been talks of hydrogen fuel cells for passenger vehicles. The case made perfect sense. Batteries were not quite powerful enough, and fuel cell offer a much longer charging range. The problem of that is that batteries eventually caught on as well.
Hmm.
And what emerged more and more recently is that fuel cells are really good for the case study when the batteries will never be large enough. A very exciting application of fuel cell at the moment, which is under development but early stage, is fuel cell for aviation. So aviation generates in the 2 to 5% of CO2 emissions in the world, just aviation alone. And if you're looking at a plane, for example, I live in Australia, or 10 to 10-hour plane at least to get anywhere out of Australia, you're looking at an extremely heavy plane using batteries because you need to be able to store electricity in a physical battery for 10 hours. With a hydrogen fuel cell, it's a completely different game because you can store it as pressurized hydrogen, which is much simpler and much lighter. So the field is going towards where there is an actual real need for a solution that can't be met with a battery. That has been quite hard to find over the years of the shift. The field has kept on shifting towards where is it that that we can't use batteries and we need to have a clean solution.
And you worked with these twin metal catalysts, iron and manganese, and
Yeah,
what's actually going on at the
yeah.
microscopic level? You
So
know,
the way they work, so platinum-based catalysts are the one that are mostly used in commercial fuel cell, but there is
yeah.
two problems with them. The first problem is that there isn't enough platinum in the world. It's one of the rarest metals. I think there's something like 60,000 tons of platinum available in the world,
Mhm.
and we don't nearly have enough to sustain a full hydrogen economy. So there's been a lot of talks about iron-manganese carbon catalysts, which are iron-based, much cheaper. The problem we've got is they're not very stable. So they work really well. You can get pretty decent power. There's a lot of very exciting chemistries going on at the moment, but the stability remains a concern. One of the approaches that are currently emerging, getting more exciting, is having two metals instead of one, with one metal sort of anchoring the iron. So instead of the iron leaving the material, with having a metal-metal bond, essentially two metals together, you have a chance of having a much more stable catalyst. There is still
Mhm.
a lot of work on it. The catalyst we did was more of a demonstration of what could be done, but that's potentially a promising approach of having two metals instead of one. But it opens other challenges, so it's still not quite there, but it's progressing in that area.
And forgive me if this is obvious, but why does adding manganese help the iron last longer? Is it
Yeah,
like chemical bodyguard or
it's
something deeper?
basically, if I'm right on this, it's basically just having a metal bond. So the manganese is not, it degrades less, and it
Mhm.
lowers the energy. It lowers the energy that will take for the iron to leach out. So it holds it, basically keeps it in place, more or less.
And
I'm more of an engineer
you
than a chemist.
you talked about triple phase boundaries. It sounds
Yes.
technical, but to you,
No,
what's
it's
so powerful or fragile about
so
these boundaries in a fuel cell?
the fuel cell, the triple phase boundary is a really interesting concept. It's basically if to have a fuel, the reaction happening in the fuel cell at the oxygen reduction reaction, you need to have three things in contact. You need to have the oxygen in contact with the electrons and the protons. That
Mhm.
way you'll be able to create water. It may look really simple, but for instance, if there are not much protons in that area, because there is low proton conductivity, there will not be a triple phase boundary. You'll just have electrons and oxygen, so no water production. And so it's quite delicate to actually form triple phase boundaries. And initially, people like it was started emerging with like modeling people who said, "Oh, there is always a triple phase boundary." But the more work is done in fuel cell engineering, the more people start to realize by designing the fuel cell materials very well, you can increase the amount of triple phase boundary, and that can have a massive impact on the power you obtain from a fuel cell. You can have a very good catalyst, like a very intricately designed catalyst with extremely small active sites and all the properties you want in theory. But if this catalyst is not integrated well in the fuel cell and can't form enough triple phase boundaries, the performance won't be very good. And that has nothing to do with the fundamental chemistry. It purely has to do with how it's integrated into the device.
I read that you measured these reactions live while the
Yeah,
fuel
yeah.
cell is running, and that feels like trying to study a rocket while it's launching. How do you
Yeah.
even begin to do that?
So it's really tricky. That's something I've been working on for a decade. The kind of things is you want to do some measurements, some very quick measurements of trying to have a sense of how much triple phase boundary you have. So some measurements we do is called impedance spectroscopy, when we do some quick oscillations of current around operating point, and depending on the frequency of the oscillation, we can capture different phenomena going on in the fuel cell. The point of this is they're not completely instantaneous. It takes 5 to 10 minutes to do these measurements, but if you find the right frequency range, you can actually get something that's fairly quick, and it gives you a sense of how triple phase boundaries are evolving. And I think
Mhm.
one of the works we did was we changed the current density of the fuel cell or changed temperature, and we were able to monitor somewhat a sense of how much triple phase boundaries are impacting. We couldn't measure exactly triple phase boundary, but we could measure over 5 seconds time span. Okay, we have less and less or more triple phase boundary forming by changing the operating conditions of the fuel cell. But because it's
And
quite
you
hard to
managed.
actually prove directly, that was hard. That work hasn't been that much cited because it's hard to actually prove it in practice. This
Mhm.
was more of a sense of it than actual measurement, actual direct measurements. So,
And you managed to cut down hydrogen peroxide formation. Why is
so
that
we're
such a
working on
big
that.
deal for
So,
durability?
so a big deal for it is hydrogen peroxide causes two reactions at the same time. It causes carbon corrosion, and it also causes the Fenton reaction, to which iron ions are produced, and it leach and also radical reactive oxygen species are produced, and that causes iron leaching. So in the case of iron-based catalyst, hydrogen peroxide is like adding gasoline to a fire. If something may
Mhm.
have been a slow degradation rate, it becomes exponentially faster with hydrogen peroxide. So we try to reduce it. At the moment, where I'm quite close to is we understand how to do it. We haven't done it yet, but we have a better understanding of how to do it through catalyst design. But it's very difficult to actually make it work.
And if platinum is the gold standard, what's the
Yeah.
real alternative? Are the materials you're using truly scalable, or is there
So
still
the
hidden
technologies
cost?
we're working on at the moment, it will be my short answer is it will be done. I have no doubt, but it's going to be enormously expensive.
Hmm.
So
Yeah.
the problem of platinum is available. We just have to make it into a particle. These syntheses are much more complex, and it's going to take a lot of resources. There is no fundamental barrier. The barrier is engineering wise, and a huge amount of resources needed to make these materials.
Mm.
It's fundamentally much simpler to make platinum on carbon, small nanoparticles, than synthesizing a completely different thing from scratch.
And how far off are we from being able to make those catalysts at industrial scale, say
It's a
for
very
powering
good
entire
question.
fleets or factories?
Yeah, it's a very good question. So there's been about, I think, one or two demos at the moment so far in the world of this catalyst, not even at a large scale, but at a scale large enough to operate a small device. I think Ballard did a couple of, I could be wrong on the years, but a couple of years ago, they demonstrated one for, I think, some kind of like battery power charging system. And the fuel cell was that small, it was fitting in your hand. And I think there's been another paper when they've done it. But to me, we are at least we need massive government support. And we're at
Mm.
least a decade, I'd say, easily a decade away. And
Mm.
also another challenge of these materials is because the stability is not at the target you are looking for yet.
Yeah.
It's hard to scale up something that is not stable yet because you spend a huge amount of money on a plan to scale up, and then you turn out that your synthesis is still not stable. So it brings the question of when do we start to scale up materials? It's more than how do we do it, but at what point is it sensible to do it?
And how helpful is AI in this research?
There's a lot of talk about AI. Personally, and that's just my own view of it, I am extremely skeptical of AI for material design. While
Mhm.
it is a very fundamentally powerful technique, the problem of it is the samples. AI really works. It's like ChatGPT. For instance, ChatGPT has been trained by taking basically, in a simple term, all the internet of a decade. And from that, it's
Mhm.
able to talk, to answer a question. That's a
Yeah.
huge amount of information. The information we have on catalyst performance, for instance, is not quite as high as that. We don't have enough information. We may have, say, 100 research papers. And while you can train the AI on that 100, you may not get information that's actually scientifically accurate or the information you're looking for because you don't have enough data to train it on. So I think it will work very well, but people need to get to realize that the size they're looking at, while the models can be trained, it doesn't mean it's trained. The response is actually correct or is useful.
And you've used machine learning, imaging, and real-time monitoring. What's the
Mhm.
next frontier? Where do these tools still fall short?
So it's something that's a piece that I'm currently working on with my colleagues, so I can't tell you too much about it. But AI was really useful for us for image processing. So if we have a very complex data set for in that case, we're talking about X-ray images of a fuel cell or different materials, we can train the AI and we can identify really well each material in the fuel cell or in the rock, or whatever you're looking at. The big barrier there is at the moment is that you need to train the model every time you provide a new data set. It's like, let's put an example. If I am scanning a rock and I segment it very well, and then I scan another rock from the same type of material, I still need to train the AI again because the
Yeah.
contrast may not be the same, the material may not be quite the same. And so that's a massive barrier. A barrier regarding operando characterization is really how to be sure that the characterization you're doing is not impacting the degradation mechanism.
Yeah.
If I'm looking at something that's degrading in like say 60 hours, while I'm doing my measurements on it, there is always a back of our head of maybe the measurement I'm doing is making the degradation happen faster or it's changing the degradation mechanism. So there's quite a lot of work we're trying to do to make sure we are fast enough, or we try to monitor the state of the device before and after, so we can confidently say, well, we've only degraded it extra by a few percent maximum. Once you start to have more than, when you start to see a different degradation mechanism after the measurements, then we know that the measurement has had an impact. So that's really the next barrier is how do you even quantify that? Most people assume that the measurement has no impact, but that's not always true. So
Yeah.
it's quite tricky.
So, so much about this technology is delicate. The balance of atoms, the
Yeah.
degradation over time. What's the most misunderstood failure point of the fuel cell?
That's a good question. I was talking to people recently. I'm going to maybe slightly digress, but one of the least understood failure point is how is the system operation, like say you plug a fuel cell to a certain device, how is that device going to impact operations, going to impact the way the fuel cell operates.
Yeah.
So fuel cells, and the same for electrolyzer, really like working at a very stable point of operation. It's not just a rated power, it's also they like to stay at that power, they perform well at that power. If you connect the fuel cell to something which sometimes emits noise or has very large fluctuations of power, the fuel cell will struggle to cope with this kind of operating conditions. It's the same for electrolyzers. You're probably familiar. There is a big problem with intermittent power conditions for electrolyzer, literally corresponding to day and night, or even it starts to rain. We have a massive drop of power from solar panels. That will impact the way electrolyzers behave. And that may, an electrolyzer that had a very good stability for like 5,000 hours in completely stable current may only have a lifetime of 10 hours under intermittent conditions. So it's really where, in the case of electrolyzer, it's where the power is coming from. And in the fuel cell, it's what's your powering with the electrolyzer.
Mm.
For instance, if you want to power the grid with the fuel cell, the devices in between have very specific specs of power, and they may oscillate a lot more than a fuel cell can cope with. And getting how that goes back to the chemistry is a whole different game. That's people are just scratching the surface of that for electrolyzers at the moment.
So, do you ever worry that some of this innovation will stay stuck in the lab, never
Oh
actually
yeah,
make it to the
totally.
mass deployment?
Oh yeah, massively. So
Yeah.
a big part of it to me is if something is too complex to make, if no matter how well it works, and that's what I call sometimes beautiful chemistry, which is fascinating, but it may not quite work because it's impossible to scale up. So it will. That's what I call it's a scientific curiosity, like fundamentally really interesting, and they also probably will get a paper in Nature or Science because it's something really fascinating, but maybe it's not scalable at all. So there is a very big worry about that. The group are working, we're very much focusing on can we put it in a device? We don't necessarily put it in large scale, but can we do it? That's what
Yeah.
we work really well with. It's very
And,
scary sometimes to see research when we can tell from the first 2 pages that it's never going to be put in a real device. It's too
yeah.
complex.
So, if we asked, say, 10 scientists to design the perfect fuel cell, how
Yeah.
different would their answers be from yours? Is there even
So
consensus in this field?
that's very tricky. I think they will, depending on what they work on, so they will give you different answers. So something really interesting with fuel cells is and it's the same in electrolyzers, is there's very much scientists that work on different aspects of the fuel cell. So one type of scientist may be really good at making flow fields, which is how gases flow into the fuel cell. And so their expertise would be designing flow field, and they will have a whole group specialized on two-phase flow simulations. Really good work in that area. But these scientists are quite different from the experts of making gas diffusion layers. So they don't necessarily, these people don't necessarily work together.
Mm,
And the problem we found recently in our paper we did in Nature Communication is that the properties of one material are impacting what's happening at the next material.
yeah.
So the very difficult part is how do you address a challenge across different length scales?
And,
If we look at water production, it's produced at a catalyst, but it's going to build up all the way to the exhaust of the fuel cell. How do you deal with it? It's very complex. So it's very hard to answer.
and you said you're now trying to, get the scientific part and the companies closer,
Yeah.
industrial part. How that feels, you
So
know?
that was a journey. That's why I was the chair of the Hydrogen Society of Australia for 2 years, and that was difficult. That was very difficult. The
Yeah.
problem I found the most, and that was the feedback I received from a lot of industry people, is that they didn't quite get what they're looking for by the lectures from academics.
Hmm.
And I think something that is not asked enough of industry, and sometimes it's a different dialogue, different expertise, is what exactly do they want to learn is the biggest question. So
Yeah.
something that's good to do, but it's hard to get good traction is I literally, before running a course, asking people, what information do you want? What do you need to learn? And academics always have the answer because they have their answers, but in industry, they may not quite know the problem they're facing. And so it's very hard to know what do you want to learn? What is the technical aspect you want to acquire more skills on? While you don't want to be lost in the research phase, the research details that are way too complex, but not giving you the answer you're looking for.
Yeah.
Yeah, we
So,
hosted the CTO of Haisata once, and that was the feedback we received. While his talk was really good for equalizers, a few people said they still didn't quite get the knowledge they were looking for,
mhm, yeah.
which was really interesting.
So, do you see, these two articulate in a certain period?
So the best way to do it is really increase dialogue, and it
Yeah.
is getting better. A lot of this comes from academic-led courses, but targeted directly at industry. Not an
Mhm.
academic giving a course that he's given before to a conference, but something that's really targeted
Yeah.
for industry while knowing this is what we want to learn. Like I think once when arrived in Australia, I gave a course on fuel cells to a head of R&D, and it turns out that was extremely difficult because I didn't know exactly what he wanted, and he didn't exactly know what he was looking for either. So it was very difficult.
Too many unknowns.
Too many unknowns and different dialogues, different backgrounds completely. So it was quite an
Yeah.
interesting task to do.
So I'm curious, do you think we as a society are asking the right questions when it comes to energy and climate, or are we just chasing the wrong metrics?
That's a good one. That's an interesting question. I would say we are slightly asking the wrong questions. The
Yeah.
bigger question we have to ask ourselves to reach net zero is how far are we willing to do to change our practices?
Yeah.
Like we only have one. Even if we scale up, if we want to consume the same amount of energy, even if we use cleaner fuel, we still will have waste coming from somewhere. We may reduce it,
Yeah.
but there will still be waste. If we decide that we want to really lower our energy consumption, then we have a better chance of solving the problem of reaching net zero.
Yeah.
It's
And
not just
you know,
going cleaner, greener, it's also changing what we're doing completely.
and there are so different opinions, and of course
Yeah.
there are different interests, and it's a jungle when it comes to the
Yeah.
information, to be
Oh yeah.
honest, and you know that. And
Yeah.
what is the right way to have this dialogue? Because
Yeah.
at a certain point, we need to stop, negating each other.
Yeah. Yeah.
I've seen a lot of people who don't want to talk to other people because
Yeah.
they are not having the same opinion,
Yeah. Yeah.
and and they're just like, no, we are better than that. So I
Yeah.
don't think that's a way. And
Yeah.
how do you think we could approach that dialogue?
Yeah. That's a tough question. There was a really good figure I saw recently about this, in a paper, which basically showed that the best way to do this is try to decarbonize every process, but you may not be
Yeah.
able to do it fully, but try to do the best you can. And that
Mm.
goes all the way from industry who have furnaces to fuel cell to electrolyzers to you can't make it completely green, but you can improve everything you have. And so if
Yeah.
you work independently but focusing on improvements without
Mhm.
judgment, without okay, well, you shouldn't be using fossil fuel. Well, some process will not be ready to move from fossil fuel for a decade. So they still have
Yeah.
to use fossil fuel, but how can they make it cleaner? Can you trap the CO2 emissions? Can you sequester them? Can you turn them into something else? Basically, how can you make everything work together to make it all generally cleaner?
Yeah.
That's my
I've
answer, but it's
discovered.
it's tough. It's tough.
Yeah. I've discovered that there is a big discrepancy between academia and the people from the industry who have different opinions,
Yeah,
and that's hard to get the peace with. So,
absolutely.
and what's the personal cost of being this deep in the energy world? Time,
Yeah,
stress, belief. What's been hardest to hold?
I don't know. To me, the hardest to hold is seeing companies that just failed completely.
Yeah.
It's very tough to see it. It's like it doesn't mean that they had the wrong technology, but it may
Yeah.
mean they identified the wrong market or that they went with the wrong direction because they went full on something on one application it didn't work. And we see that all the time with the electrolyzer company. We see
Yeah.
them grow very quickly. And another problem with all this field is that the industry is starting to be bigger than the demand of it.
Hmm.
So it's quite a lot of companies emerge quickly, but the market
Yeah.
is not as big as we think. There is lots of promises to grow, but in practice, number of projects are not that big, are not that many yet.
Yeah.
And
And
another
where do
problem
you?
we've seen is the complexity of setting up the systems.
Yeah.
Setting up electrolyzers take decade to do a project.
Where do you see the solution for this?
I think again, it's through more and more dialogue. That's the biggest solution. Another part is if you have a project on electrolyzer,
Yeah.
involving the company as early as possible. Like if you
Mhm.
know your project may take a decade to be built, you may want to look like a company who has the promises to be there when you're ready to do the project. So planning them much earlier stages for the
So
project.
the offtake is the biggest problem,
Yes.
and we already have companies who are using a huge amounts of hydrogen, anyways, that is
Yeah.
created from fossils.
Yeah.
So basically, it's not, the offtake is a problem of the price. Am I right?
Yes. Yeah. Yeah. The price is the biggest problem here.
So
Hydrogen
what
is
we need,
way too more expensive.
yeah.
Yeah.
So what we need to do is actually to get the price down.
Yes. So that goes from everywhere. If we look
Yeah.
at hydrogen from solar panel, first a while ago, solar panels were extremely expensive. Their price has gone down like in a
Yeah.
decade, an incredible amount. The problem of price also goes from at some point, we'll have cut down all the costs of the system, but we still end up, and that's where I go back to my research a bit, we still have expensive materials going inside the electrolyzer or the fuel cell. For
Yeah.
instance, PEM electrolyzers, they still rely heavily on iridium material and fuel cell
Mhm.
and platinum. That's a barrier, that's a fundamental cost that can't be lowered if you want to keep using the same materials.
Yeah.
So the fundamental cost remains the fundamental issue.
Yeah.
Yeah,
Quentin, thank you so much for being my guest today.
that was great. Thank you.